Hi there. With 5-axis printers and non-planar printer instructions, you can print parts like this without support material. In this video, I'll show you how I printed this part with the 5-axis printer and explain what they are and why almost nobody has one. First of all, what is an axis? And how many of these are in your typical 3D printer? If you haven't already guessed, the term axis, when used in the context of a machine, is similar to an axis as defined in your run-of-the-mill high school math class. To define locations in three-dimensional space mathematically, we define three linear axes, the x, y, and z axis. In the physical world on the printer, this also means we need at least three axes to move the hot end to any point we want to extrude hot plastic at. On this printer, we have the x-axis, the y-axis, and the z-axis. Conventional 3D printers are still limited to movement in these three linear axes, from the cheapest $200 kit DIY printers to the most expensive industrial FFF printer. A 3-axis printer allows for low-cost construction and simplicity in the generation of the instructions needed for the printer to print a part. For example, if you want to deposit material at a certain position in space, you just have to specify the coordinates that you want to go and how much to extrude. Machines with more axes actually need more information than just these position coordinates. There are some drawbacks to printing with planar layers though. FFF is known for being weak along layer lines. You also get stair-stepping effects when you print curved parts along the z-axis. And support material is material that gets thrown away and takes time to print as well as remove. Enter 5-axis printers with non-planar slicing. They have the potential to eliminate a lot of these drawbacks.
Printing parts using non-planar pathing and 2 additional rotary axes, you can print shapes with extreme overhangs without support material. This means faster build times, less used material, and less post-processing.
As you can see, on this printer there are 3 linear axes and 2 rotary axes. Instead of moving linearly, they actually rotate about an axis. This allows the printer to rotate the bed around the printed object, making overhangs that were drastic more manageable and allowing access to previously printed layers by rotating the part underneath the nozzle. Adding these 2 rotary axes is a common step for 5-axis milling machines that allows for good accessibility to the part the machine is working on. 3-axis machines aren't commonly used with non-planar printing as they lack this accessibility when moving in non-planar moves, severely limiting the strategies that can be used. CNC Kitchen has a great video on a non-planar technique with 3-axis printers.
Printing in layers that aren't planar can also make parts stronger in use by printing the layer lines, the weakest part of a print, in an orientation such that it doesn't experience the highest forces when the object is in use. In this example, the layers follow the curve of the part, which doesn't optimize the part for strength, but this toolpath strategy allows this part to print without any support material. Printing in layers that aren't planar also allows for toolpaths to follow the curves in the geometry of a part, especially on the outermost sections. This allows for better surface finishes on parts that would otherwise exhibit stair-stepping. Michael posted this example on his Twitter account. This is an example of a print where the top surface is printed with non-planar G-code and is still feasible to be printed on a 3-axis printer because it doesn't require a great deal of clearance to print it. You can see here a comparison of the same part that was printed with layer-by-layer printing approach.
This technique can also be used with a conductive filament to lay down traces to complete circuits on a 3D print as well. Freddie, the creator of the Open5X project, has a video showing this application. So if 5-axis printers have so many cool benefits, why aren't we all currently printing with them? This is for multiple reasons. The first main reason is that the 2 rotary axes add additional cost. The second main reason is that having 2 more axes also reduces the rigidity of the machine. What was once a very solidly mounted build plate is now smaller and flexes more because designing it to move means that it can't generally be supported as easily by the printer's frame. Third and most problematic is that there aren't easily available slicers that will create instructions for 5-axis printers. Printing apart layer by layer is a relatively simple approach to create instructions for a printer. But 5-axis printing requires algorithms that are much more complex. This is because when we send commands to a printer with more than 3 axes, we need to send more than just the position information. We also need to send the orientation information of the nozzle. The lack of adoption of 5-axis printing resembles the chicken and egg problem. Because there isn't software on the market to make instructions for a 5-axis printer, companies have no reason to make hardware for it. And because no companies make hardware, there isn't a pent-up demand for creating the algorithms necessary for slicing 5-axis prints. If this is the case, then you may be asking, how did I print this part?
Despite these challenges, some 5-axis printers do exist in the hobbyist market, notably 5-axis Maker. Additionally, a project called Open5X by Freddie has created the first open source hardware project that modifies a Prusa i3 with an additional 2 rotational axes. Other makers, like Brendan Builds on Twitter, have created additional 5-axis hardware and added it to the project, enabling 5-axis beds to be installed on the Voron Zero and E3D tool changer printers.
To try it out for myself, I made a design to convert my tool changing Jubilee 3D printer to use the build plate that Brendan Builds designed for the E3D tool changer. If you happen to have a Jubilee 3D printer, I also contributed this design based off the Jubilee's original files to the repo. On the software side, there are currently a couple approaches to make the instructions for your printer for non-planar and 5-axis printing.
Freddie of the Open5X project has also created an experimental conformal slicer that follows the shape of an input part in Rhino and Grasshopper. This allows for generation of G-code from a model file, but is limited in its current scope. To create G-code for the printer, FullControl is a project by Andrew Gliadol and Dirk Elias that allows the user to design G-code geometrically using functions in Python. This is useful for programmatically generated parts, but don't expect it to create G-code from a model file from printables. Another repo of this project exists called just FullControl G-code Designer that uses Excel if you aren't well versed in Python. Renee Mueller has been experimenting with slicers for some time and has developed an algorithm for conical slicing based off a model file. Renee Mueller also built on methods proposed by researchers for creating non-planar G-code from planar algorithms by transforming model files before processing for G-code. A very interesting read.
5-axis hardware for printers allows for many different techniques for generating layers and paths. Each technique will have its applications, and a technique that is accepted to just work to slice model files hasn't been developed yet. Optimizing for part strength using non-planar layers is even further away, as an analysis of the forces on the part needs to be done before slicing, and then it needs to be integrated into this non-planar slicing toolchain. A discussion of non-planar slices wouldn't be complete without talking about industrial slicers. There are some industrial slicers that create G-code for robots and other 5-axis machines, but these products are specialized, require training, are closed source, and are very expensive. So, how do we all get 5-axis printers? We've covered the basics of 5-axis printers and non-planar pathing, and its potential to improve our prints, as well as the hardware designs are here, but the software is still catching up. So how can we advocate for advancements in state-of-the-art so we can slice non-planar parts as easily as we can slice with planar toolpaths? If you are interested in non-planar printing, start experimenting with it. If you have a printer that has designs for a 5-axis bed in the Open5X project, you can retrofit your current printer and play around with some of FullControl XYZ's 5-axis demo G-codes they have on their website. If you're feeling really adventurous and have CAD skills, you could improve the current hardware designs or contribute to the documentation on GitHub so that more people can get involved. Thanks for watching this video, and let me know your thoughts in the comments below. See you next time.